Coming into this course, hopefully you had an opportunity to work on what's called partial fraction decomposition, or what else referred to as PFD for short. So partial fraction decomposition is effectively the process of taking a fraction and decomposing it, which sounds dramatic, but all it means is trying to rewrite that fraction as a sum of a number of partial fractions, if you will. That is to say, we're trying to figure out, okay, if we know that this here can be rewritten as 5 over x plus 3 times x plus 1, which I get by just factoring my denominator here. If I know that this is that, then I can actually just rewrite this. Let me actually just move this over here, right underneath. What I'm effectively trying to do is I'm trying to figure out which two fractions, when I add them up, will give me 5 over x squared plus 4x plus 3. And so we set it up as such. And I will link my video on partial fraction decomposition, which is pretty extensive and goes through a couple of the different strategies and techniques for doing partial fraction decomposition. Uh, in essence, it really just refers to or relies on using systems of equations to do this. Now, this can get a little tedious and unwieldy. Fortunately for us, there is a method developed by a mathematician named Oliver Heaviside. And so what I want to emphasize here is what's called the Heaviside approach, right? It's a pretty dope name if you think about it, the Heaviside approach, or the Heaviside method. So we're going to use Oliver Heaviside's method for doing partial fraction decomposition. Now, this has some limitations, which I'll talk about in a bit, but let's just go through the approach here. So the method effectively is this. We are going to multiply both sides of this equation that we've set up here by the least common denominator, which is x plus 3 times x plus 1. In doing so, this left side will just be equal to 5. This right side, if I multiply all of this by x plus 3 times x plus 1, this becomes a times x plus 1 plus b times x plus 3. Now, where we would normally set up a system of equations from here, Oliver Heaviside just pretty much said, nah. Instead of that, what can x be so that this entire a term would be eliminated? Well, if x is equal to -1, and I plug -1 into this equation, I then get the left side is still equal to 5, and the right side is equal to -1 plus 3, which is just 2. So that is to say, not plus, but equals, b is equal to 5 over 2. Then rinse and repeat that for the other one. If I want b to go away, or b to be eliminated here, what would x have to be? Let x be equal to -3. When x is equal to -3, 5 is equal to a times -3 plus 1, which is -2. Therefore, a is equal to -5/2. And what that effectively then allows us to do is to substitute those values back in. A is equal to -5 over 2, and b is equal to 5 over 2 times x plus 1. I know, amazing, right? So this Heaviside method actually saves us quite a bit of time and allows us to figure out the partial fractions a lot more easily. Now, Oliver Heaviside's approach, I could leave that there, but Oliver Heaviside's approach does have its limitations. It doesn't work when we have the degree of the numerator being greater than the degree of the denominator, or even when the degrees are the same. It also doesn't work when we have repeated linear factors or even quadratic factors. So it really only works when our factors in the denominator are linear, right? When the factors are linear, and the degree of the numerator is less than the degree of the denominator. The good news for us is that nearly every partial fraction integration problem that we do in this course can be done using the Heaviside method, which is awesome news. Now, in doing all this and talking about the partial fraction decomposition process, I haven't really spoken yet about why on earth we would ever do this. And the answer is pretty simple. Because what if I asked you to integrate this function? If I asked you to integrate 5 over x squared plus 4x plus 3, you might look at that for a little bit, but then realize there's actually no other method that we've discussed in this course that would allow us to integrate this function easily. But, however, we do know how to integrate let me just go ahead and copy this. It's equivalent fraction decomposition. That is to say, if I ask you to integrate this, this is certainly something that we could do. We would say that this is negative 5 over 2 times the natural log of absolute value of x plus 3 plus 5 over 2 times the natural log of x plus 1 plus c. So we do partial fraction decomposition because it allows us to take a fraction that was previously difficult to integrate, and now by decomposing it and breaking it up into smaller fractions, we can actually integrate each one of those fractions individually. All right, so let me go ahead and do maybe one other example of this, just so we can really practice that decomposition. Okay, so let's maybe do something like, let's go to try this second problem up here. All right, so let's do the decomposition. So the first thing I'm going to do is I'm going to rewrite this integral using the decomposition form. We're going to say it's a over and b over some factors. So this is pretty easy to factor. We got x minus 5, x plus 2, dx. All right, so we just factored the denominator, split it up into two fractions, and we're trying to figure out what a and b are such that the sum of these fractions, these partial fractions, is my original integral. So if I multiply both sides by that denominator, I'm going to get 7x is equal to a times x plus 2 plus b times x minus 5. And using the heavy side method, I can just let x be equal to the value that would cause this term to be eliminated, so that's negative 2. So that then gives me negative 14 is equal to negative 7b. Therefore, b must be equal to 2. Let's do the same thing now to eliminate the b term. So let x be equal to positive 5. So 35 is equal to 7a. Therefore, a is equal to 5. Plug those back in to our original 5 and 2. And now we can integrate this. Let me just move that over here. So what is this integral? Well, this is simply just going to be 5 times the natural log of the absolute value of x minus 5 plus 2 times the natural log of the absolute value of x plus 2 plus c. Okay? And that is integration using partial fraction decomposition.